Hi, friends and colleagues. We sincerely thank everyone for joining our Responsible Data Summit. I'm Vivek Sharma. I'm a researcher at MIT working on contact tracing with Ramesh Vaskar. Along with that, I'm also a researcher at Harvard and KIT. So the Responsible Data Summit is just a beginning. It is a platform where we bring diverse community working towards privacy and data economy. Starting from 28th until 30th July, we have two tracks, which has been basically broken down to 3 days. So on 20th and 29th, which 29th is today, so where we emphasize how we utilize the responsible data to help COVID-19 and the future outbreaks, epidemics, and pandemics. On 30th, we will emphasize on state-of-the-art technologies for privacy, AI, such as split learning, federated learning, and also the non-technical aspects from the policymaking side for responsible usage of data. In all, we gather roughly 50 influential speakers from intersection of both academia and industry, where they come from similar mindset of data usage or responsible data usage. We also would like to thank our approximately 1,200 attendees for being part of this move. Our summit is basically driven by two objectives, the general accessibility and sharing knowledge of a state-of-art technologies with the general population. We try to make our event generic by bringing community and people coming from technology, policymaker, health, and so on. So I would like now to thank upon our organizing committee. Without Don, Ramesh, and other committee members, it was not possible. And the other coordination committee. So the agenda of our current plan is that it is broken down into basically in 6 segments. Basically, we start off with GAN and government, which Ramesh, Frank, and David are going to handle. And then we have other talks and tasks that I will walk you through it as the session comes. And we have people coming from different community, and they're going to share their knowledge in different aspects of contact tracing and COVID-19. Now, I would like to invite upon Ramesh, Frank, and David. Thanks.
Thank you, Vivek. What an honor to have you all as part of the Responsible Data Summit. I'm Ramesh Raskar, professor at MIT, and a lot of my own research is at the intersection of digital health, machine learning, and privacy. And I have been involved in contact tracing efforts for quite some time now. And I'm delighted to have Frank Moss, who's the former director of MIT Media Lab, and David Kong, the director of the Community Bio Initiative at MIT, also join and talk for a few minutes about the role of Google optical exposure notification, case management, and the role of the government. If you think about National Weather Service and how it allows us to deal with crisis like the hurricane, can we have a similar mindset when it comes to a pandemic? For a hurricane, you need two things. You need the bird's eye view, literally the satellite, and you also need prior models of the hurricanes. For epidemics, unfortunately, it's more challenging because it's innocent people infecting other innocent people. So to create the bird's eye view, we actually need participation and coordination amongst the residents themselves. And this is where smartphones can play a very important role, but then we immediately run into issues of privacy, adoption, connection to public health, and so on. I was very fortunate to be invited by the US Congress for a congressional testimony about 3 weeks ago. And I had a chance to talk to many key players in the government and outside. And it's very obvious that we need a form of a coordination very similar to National Weather Service, but that relies on individuals participating in it. So today's session is really about how we're going to think about various pieces of this puzzle, from apps to servers, to epidemiology, to standards, to data challenges, and so on for today. And over the coming weeks, we'll be talking about non-technical issues as well, such as epidemiology, connections to public health, and so on. So let me hand it over to Frank Moss to hear his thoughts. And Frank Moss is a legend because he has worked on many national initiatives, also is the former director of the MIT Media Lab. Frank, over to you.
I'm not sure how happy I am being called a legend, but I appreciate it, Ramesh. I first first of all, I'm honored to be here, and thanks for the invitation. A great group of folks has been assembled. Very important topic, unbelievably important. First met Ramesh back in 2007 when I was director of the Media Lab, and I have the honor of having hired him as one of my first junior faculty hires and watching him grow. At the Media Lab, we became heavily involved in digital health technology. And after I left the lab, I formed a number of companies to pursue that, but sold the last one in 2018 and kind of got out of the digital healthcare business when I got a call from Ramesh about 3 months ago. And he said, you got to get off the sidelines right now. You're quarantining down in the Cape. And we've got some very important stuff going. And Ramesh told me about what was happening with exposure notification, digital contact tracing. And I was particularly excited to hear that Apple and Google, in an unprecedented move that I've never seen in my 35 years, had gotten together so quickly to agree on common API and protocols to enable applications to be built. And I found that very compelling. So I said to Ramesh, let me join up and see how I can help in this in any way. And what I observed in studying the area with Ramesh and his team at PathCheck and others is that the road from the kinds of technologies that you folks are developing, the interfaces, the Bluetooth technologies, the key servers, and so forth, to actually having that implemented and have an impact on health of populations is a long and a hard one. And it reminded me a lot of the work that I did some 20 years ago to bring the Broad Institute of Biomedical Health into existence. And that was the notion that moving from sequencing to actually having drugs and medications in the world impacting patients is a long road. And I began to think with David and Ramesh about what new kinds of institutions would be required. And very much so interdisciplinary. We have to bring together people not only in public health, technologists such as yourself and other public health folks who are on the call here, behavioral economics, public policy, into new kinds of organizations that can help move from the technologies to actually impacting public health authorities in states and around the world. So without going into details, I've enjoyed working with Ramesh and his team with David on trying to understand what kinds of convening would be required to actually move your technologies into scale, into the world to have impact on populations. And again, congratulations on what you're doing here, and we look forward to talking about that more in the near future. So with that, I'll turn it over to David.
Thanks so much, Frank, and also Ramesh. It's truly an honor and a privilege to be here. My name is David Sun Kong, and I direct the Community Biotechnology Initiative at the Media Lab at MIT. So very much like Frank and Ramesh, have a very strong Media Lab DNA, which again, I think connects very strongly with the larger interdisciplinary effort that we believe is really needed to ultimately successfully implement these very powerful and really life-saving digital technologies. And so in terms of my own background, I'm a synthetic biologist by training, working in microfluidics and lab-on-a-chip technologies, a community organizer, a social justice activist, and more recently, a researcher in collective intelligence. And so a big part of my work has been studying the ways in which very diverse communities can drive innovation. And so a big part of that work has been involved in this larger movement around what's called community bio, which is really about democratizing biotechnologies and ensuring that there's equitable participation in the life sciences. And through that work, again, I think we've really learned so much about the power of interdisciplinary research and the power of diversity in bringing together groups to solve these complex problems. And as Frank has already illustrated, I think that's very clearly what's necessary when we think about digital contact tracing and a lot of the technology problems and solutions that you all are working on here. And something that we've learned over the past weeks and a couple months in really surveying and understanding this space is really the idea that this is more than just a technology problem, and that these diverse stakeholders that Frank mentioned, including public health experts, government officials, the technologists, science communicators, and so on, are all really necessary and need to be brought to the table. And that significant education initiatives need to be undertaken. So in order to get the various stakeholders and government officials to understand the latest technologies and understand the complexity of the technology management issues, a lot of work needs to be done there. And again, significantly, tremendous coordination is required both at the state level and also at the national level. Currently in the United States, there's an initial pilot for some of these technologies that's being implemented in Minnesota, but there's still a tremendous amount of work that needs to be done. And in addition to all of these technology management issues, we really need to, perhaps in an unprecedented way, establish different types of new partnerships between public health, between government, between private institutions and nonprofits. And again, I think there's a lot of great evidence looking at what's happened with Google and Apple that we're really moving in the right direction. But so much more work is needed to happen. And particularly when we think as well about issues like adoption. How do we ultimately get these apps onto phones? And as I think will be discussed a little bit later on today as well, how do we engage with communities of color and folks that really have been suffering disproportionately in the pandemic, and ensuring that they're also part of this ultimate technology solution? So again, I think there's a tremendous amount of work that's ahead, but it's been really exciting to learn so much about this space and to engage both with Frank and Ramesh, and really all with you, with all of you as well, in developing these technology solutions that ultimately we hope will really save lives. So it's an honor to be here. And again, Ramesh, I'm very excited for today's event and to hear from all of you about the technologies you're developing today.
Thank you, Frank, and thank you, David. Definitely a great start. We have a lot coming up. So let's move on to the next session. So let me introduce Scott Baker, the CEO of Association of Public Health Laboratories, Nate Johannes from Microsoft, and Jeff Day from Microsoft, to talk about how GAIN can really be supercharged by having a Bluetooth server. So let me hand it over to Scott.
Thank you very much, Ramesh, and thank you to all of the organizers and also to all of you who are contributing this effort from the tech side. I think a big thank you from public health, and to follow on what David said, this is a big community. Everyone's working together. 6 months ago, I never would have believed we would be doing this right now, but it does take a village, and we're all in it together. So thank you very much. What I wanted to do was to answer one big question, which I know a lot of people are asking, which is why APHL, and who are you, and what are you doing in this space? I'd like to give some background about the informatics work that we do. So let me start with the organization's vision and mission. We at the Association of Public Health Laboratories believe in a healthier world through quality laboratory systems. And we, in the laboratory community, and we do represent state and local public health laboratories and their parent agencies, which gives you a sense of why we're involved in this. We think of things in terms of systems. And I know that you do as well. We're part of a large ecosystem for contact tracing, exposure notification, diagnosis management, et cetera, et cetera. And that's really what we're looking at, is how can we improve the world through these systems? And our mission is to shape national and global health outcomes. And we do that by promoting the work of our members. So in this discussion, we're not talking about a laboratory technology, although at the end of the day, contact tracing will hopefully lead to somebody getting a accurate diagnostic at the end of this. And hopefully someday they won't have to wait many, many days for a result. But when I think of what we're doing here, we are looking to improve public health practice. And you are looking to improve public health practice as well. APHL sits in the middle of national and global dialogues around public health policy, public health and laboratory science, and practice. That's our sweet spot. Let's go to the next slide. APHL in the public health space is largely known for our science work and also our informatics work. We do host something called AIMS. The discussion that we'll have and Jeff in a little while, it really is not AIMS that we're talking about them. I want to differentiate it. But APHL hosts the APHL information messaging services, and it is a secure cloud-based environment that accelerates, you can read it for yourself, the implementation of health messaging. So when you think back to last year's flu season, and every week you saw on the news what the flu statistics were, right? So that data was powered by APHL, was powered by AIMS. That data comes from public health laboratories through our cloud onto the CDC and there for public consumption. So we do that by providing shared services for transport, validation, translation, transformation, and routing of electronic data. Now notice I didn't say lab data. So this is where APHL becomes like the silent L, if you will. We spend a lot of our effort thinking about connecting public health systems with public health data and exchanging that data. And that is really on behalf of public health agencies. So that's just give you a sense. Again, this is not built on AIMS. It has nothing to do with AIMS, but informatics and lab informatics and electronic data messaging is in our DNA. So the next slide, please, gives you a very brief description. Actually, it is in this slide, but that's fine. AIMS, we like to think of AIMS with its, we can just stay here, with its many use cases as a national HIE, if you will. So we are a national resource for public health. We're connected to every state health agency. There's a number of CDC use cases and other public health organizational use cases, as well as some laboratory clients that work through us and with us and are able to exchange their data quickly because of us. So the next slide. This is the functional architecture. You're seeing this very briefly, just to give you a sense that AIMS is both a platform, it's a hosting solution, and has a variety of services that we provide wrapped around important structures of system management and security and information access. We have all of the requisite government approvals, and we're in FedRAMP, and we're HIPAA compliant, and all of those things. Again, not necessary for exposure notification, but just to give you the sense of APHL is deep in the public health information exchange space, and exposure notification is an important new technology for public health. Next. So the platform, again, has messaging services. It is a platform for data storage, and then we have support. We are involved in different use cases across the country. A lot of these are funded by CDC, but not exclusively, but they are all public health oriented. The data I'm showing on the right is actually very low now, given COVID and given the amount of data that's actually passing through us. But I want you to really focus on that middle point, that we have a deep understanding of public health needs and the landscape. That gives you the reason why APHL stepped in on behalf of the public health community to say, we'll host this, we'll interact with Apple, Google, and Microsoft and others to support this exposure notification server. Because what we have is the connection to all 50 states. States came to us, public health organizations said, this makes the most sense. So we worked very quickly to understand what the needs were. We've been engaged with a variety of different efforts to do that. But the key word here is this deep understanding, and what that really translates to is trust. And that is the key thing here. And you spoke about that earlier in the opening. We've got to instill trust in our government institutions, in our scientific institutions. There's data privacy concerns. There's a lot of concerns. We've got to build out the trust. And that means really working together to be able to do that in a very transparent way. Next slide. I want to just give you a sense of what we've been doing in the last 6 months on COVID-19 in and of itself. So these are individual use cases that we've been involved in. And exposure notification is down on the bottom. And that's because it's one of the more recent ones. So we've actually been in the COVID data exchange IT space for as long as we've had COVID. The very first thing we did was we built out the pipeline for public health laboratories to begin reporting data federally to CDC, much like we do with flu data. And I'll walk through that in a minute. But we work to improve the workflow at the laboratory level. And when I say the laboratory, at the public health laboratory level, there are 98 public health laboratories across the country, state and local, that are able to test for COVID. They were the first in the country to do that testing once the test came out. FLIP is the second use case. That's where the flu data goes through, but this is now test result data that is for COVID. And this has been the most streamlined effort in the country to have data flow to the federal level. It's been the most consistent approach to data, and that's because we've worked to build this over more than 10 years. We've been working on electronic case reporting, which means taking data from electronic health records, the electronic health record systems at clinical settings, bringing that to a knowledge management system, and working through that knowledge transfer, and then moving that to electronic case reporting. So we're moving away from paper-based, we're moving away from sending spreadsheets. One of the challenges in public health, and it's never been seen as publicly as it has been through COVID, has been the lack of investment in public health data and surveillance systems. Now, APHL and our colleagues at the Council of State and Territorial Epidemiologists and others recognized this a few years ago, and we stood up an effort called Data is Elemental to Health. It was both an advocacy campaign and a public awareness campaign on what was needed to improve public health data. And we were successful, and we received, we, meaning the public health system, received funding for the first time from Congress last year. Since then, with the CARES Act and subsequently, I think we've all recognized the need to improve those data systems. But electronic case reporting is one of the things that we've been working on for a while. You can continue to go down the list yourself and see this, but these data feeds are coming from public health agencies to CDC up to HHS. We are working with individual laboratory manufacturers, test developers, et cetera, on direct device reporting. So we also are hosting the SARA Alert app, which is more on the symptom tracking side of the continuum from exposure notification, contact tracing, and then symptom tracking. And then it comes to hosting the national key server for the exposure notification system for COVID-19, and guaranteed, because we know this is not a static situation. There will be a lot more that we will be involved in. Next slide. Just to give you a sense, at the upfront, I said the very first thing that we started to do was to work on the LOINC codes and to get those ingested in the laboratory information management systems so that they could be reported out in a clean way. And we were very successful. Between January 30th and March 26th, every state was able to do this. So we spent a lot of time. We have I'd say a small but mighty staff that work on this, and it's really what is powering the laboratory data from the public health sector in this country. And it started on January 30th. Next slide. Just to give you a sense of the electronic lab reporting that we've been doing, this just gives you the sense from October of 2017 through July of 2020, and where that where those numbers are, what the usual flu season might look like. You can look at those bumps from the December to April timeframe of 2017, well, 2017, 2018, and then you can see where we are in 2020, and the flu season hasn't started yet. Next slide. So what we wanted to do at this point, I wanted to turn this over to Nate Johannes, who's our partner at Microsoft. APHL, in order to accomplish this task, we needed to turn to a partner, and we turned to Microsoft to work with us and to really help make this a reality for the nation on behalf of public health. So I'm going to turn it over to Nate.
Well, thank you, Scott. And I believe, Jeff, can we click over to the next slide, or whoever is controlling the slides? Okay, we got one more. There we go. Fantastic. Well, first, thank you, Scott, and our friends at MIT. We're certainly grateful to be on this call with many of you. And of course, the folks listening, we hope that this is a success in terms of articulating some knowledge, and we can continue to advance our efforts in this space. My name is Nate Johannes. I'm a Director of Technology and Strategy in the office of the CTO here at Microsoft, and I have the fortune of, again, working with Scott, and of course, working closely with my friend Jeff Day, who will be also participating on this call. I do want to articulate that I've, a lot of these discussions, especially with Scott, talks about working with public state health agencies, is near to my own lived experience. I had COVID, and fortunately, I'm here to talk about it. But certainly, my experience working with the state of Washington, which is a fantastic state, but the health agency I was lost in the machine, and so I know that there's some pain points based on my own lived-in experience, and certainly being in the position of power to help drive that, and that's why I'm very, very much enthusiastic to work alongside some of the best and brightest in the industry, including you. So, Jeff, how about we go over to the next slide, and I'm happy to walk through on a super high level how this application works, as well as Jeff, my colleague, will double click into the technical aspects of it. And so I hope that you enjoy the next 20 minutes or so of the discussion. So. The scenario is I think, pretty straightforward on its face, certainly complicated in applicability. The intent is to have an application, as Scott indicated, created or distributed by the states, which would be the central app for each state, and individuals voluntarily downloading these applications. And if one individual, let's just say that I'm talking to Jeff, and we both have this application, using Bluetooth, our keys will be just talking to each other and providing updated information in terms of our proximity. And in the event that, certainly in my case, where I've had some symptoms and I unfortunately tested positive for COVID, I would upload my data to this application I downloaded, and it will send it over into our cloud Azure, where the keys are being hosted. Scott, I'm sorry, can we hit the next slide? And from here, we're going to talk about, effectively, the individual that I've been in contact with will receive an alert from the application indicating you've been in close contact with somebody who tested positive for COVID, as well as follow-up information in regards to next steps, where to get tested, do you have symptoms, even potentially being monitored to have some check-ins from the state. So that's the pretty straightforward application of it, and Jeff will dive into the technical aspects of it.
All right. So yeah, my name is Jeff Day, and I'm a engineering program manager at Microsoft. And before I dive into the tech, I just want to say that one of the questions I'm always asked when like new people join this project is it strange to be working with Google and Apple on this? And at a kind of like meta level, it is. It's like, how often do Google, Apple, and Microsoft collaborate with a customer with like APHL? And it's not something we've done before, but the experience has just been really great. COVID has kind of created this atmosphere where everybody involved from all the different companies, the competitive nature of our kind of underlying companies just isn't a factor for those of us who are working on this project. And it's a very collegial, collaborative process. So it's really been great. What I'm actually going to be presenting here is the Google and Apple protocol. This is not something that Microsoft has developed. It is something that I've had to learn in a great deal of depth, because one of our one of the things we're really trying to do for APHL is make sure that the system is fully understood and implemented in a completely secure and private manner. We don't want to put a key server up on APHL side and have any sort of security privacy vulnerabilities. So if Microsoft's role is, obviously technical advisor and to APHL, but we're bringing Microsoft's strongest security and privacy minds to this process, so that we can assure that the privacy and security protections built into the protocol are actually preserved in the final production system. So with that, I'm going to start really at the Bluetooth protocol level, because this is really important to understanding how a security first, privacy first exposure notification system can work. So the first thing here, and I'm an engineer, and I have thought about trying to create like nice graphical slides to describe this process, and boy, it's hard. So I'm not an artist, so just sticking with some text bullets here. At the heart of this is the Google and Apple developed a Bluetooth LE protocol for exposure notification, and what's happening is simply that phones in proximity of each other exchange random numbers and store those random numbers in the operating system, in a table in the operating system. In order for that to happen, a user must opt in to the operating system will put up, show an alert that says, do you agree to let to let your device participate in this system? And so the user, this is not going to happen mysteriously in the background, and it's only going to happen if the user opts in. The current version of the solution does require that you download a state developed application before you can opt in. In theory, the Android and iOS capabilities could be enabled on the phones, just in the operating systems themselves. It could just be a system feature so that you could actually start participating in key exchange without an app being installed. But Google and Apple have made a decision that, at least for this first version, that they want the state health agency to lead, and so they're requiring that you install your local state application before you get prompted to turn on the Bluetooth key exchange. So now, to the next few moments, I'll talk about how the privacy is protected in this solution. There are also some nice tricks in here to assure that the amount of data that's actually uploaded to the exposure notification server is as small as possible. So within the exposure notification API, a core concept is this thing called a temporary exposure key. A temporary exposure key, at its heart, there's some technical metadata wrapped around this thing. So the total size of a TEK that's potentially uploaded to the server is about 30 bytes. But at the heart of it is this 16-byte crypto random number generated number. And it's just a number. it has no bearing on the identity of the user. There's nothing from the device that's represented in there. It's truly a 16-byte random number. And that number never leaves your phone, especially like when you're exchanging keys with other Bluetooth devices. That number is just stored locally on your device. There's one of those numbers per day. And then what the OS does is every 10 minutes, it uses a hashing function, which consists of the random TEK number and the current rolling period, which is a 10-minute interval. So midnight to 10 after midnight is rolling period 1. 12:10 to 12:20 is rolling period 2. So the TEK with that rolling period number is hashed, and it produces yet another random number, which is called a rolling proximity identifier. The rolling proximity identifier is the value that is exchanged with other devices. When another device receives an RPI from your phone, it simply stores that RPI in a table within the operating system. The RPIs are never visible to the application or to any user. It's just internal data stored by the operating system. Okay, so one other privacy-preserving piece of functionality is that your actual Bluetooth ID that's being used to trade, to exchange RPIs rotates every 15 minutes. And this is designed to prevent an attack where somebody would actually capture your RPIs and store your Bluetooth ID, and then try to map RPIs together based on correlating them with a Bluetooth ID. A key point about this thing is because the TEK is the seed for all of these RPIs, when somebody reports themselves as positive, only the TEK needs to be uploaded to the national key server. So at a high level, this is the architecture. Each state is going to create its own applications, one application for iOS and one application for Android. Google and Apple actually have a policy that each state only gets one application. So each state needs to designate a single public health authority that will develop and publish the app for that state. We're seeing kind of predictable behavior, which is there are certain states that are taking the lead in developing exposure notification apps, and other states are asking to work with that state and reuse their application. So as an example, North Dakota is going to be the first state to go live on the national key server, we believe. And North Dakota has formed a consortium with South Dakota and Wyoming that plan to go live with reusing the North Dakota application. South Dakota and Wyoming will still publish their own apps with content from their public health authority in those apps rather than the North Dakota content, but the core application and functionality is being created by a developer that has partnered with the North Dakota Public Health Department. The state of Washington is really viewed as a leader in public health technology and best practices, and they are currently running a trial with their own private key server to basically validate that the system works, and also to do some studies around the efficacy of the solution. We expect that their solution will be picked up by other states in the Western US. We've already been talking about the API. A key part of, this slide shows the verification server, but I'm going to jump first to the national key server. The way the protocol works is when you receive a positive diagnosis, your application gives you the option of reporting yourself as positive. And this is something that is going to require a lot of education. There, many folks who I've spoken to about this solution are very concerned that reporting yourself as positive somehow will not be a private act and expose it, potentially set you up for, for some party to discriminate against you because of your positive notification. The whole random nature of a TEK and the fact that it can't be traced back to you is designed to defeat that. So this very much is going to be an educational thing for the public. But ultimately what happens is when you report yourself as positive, your application will upload all of the keys that it's collected or that it's generated for you to date, up to 14 keys. The keys, the device only stores 14 days worth of keys, and as older keys exceed 14 days old, they're removed from your device. So when you report yourself as positive, all the keys on your device up to 14 will be uploaded to this national key server. That national key server then aggregates all the keys of positive patients that have reported themselves together into a signed file, and that file is then distributed over a content delivery network back to all of the apps. So the apps once a day will download the latest keys that have been published on the national key server, and then the apps go through each key in there, compute the RPI for every one of those keys, and they can optimize that by only computing the RPIs or computing RPIs for the times that they've received and stored keys, and just do a lookup and say, hey, have we been anywhere, or has this user been anywhere near somebody who's been reported as a positive, or who's reported themselves as having a positive case? And if the answer is yes, the operating system notifies the app, and then the app is able to go through a public health authority designed situation that says, okay, we're notifying you that you potentially have been exposed to COVID because on Tuesday or whenever the match happened, you were in proximity for 10 minutes, 20 minutes, 30 minutes to someone who's reported themselves as positive. Here's what you should do next. And that's the kind of what you do next functionality is something that each public health authority needs to design. And for example, that's what the University of Washington is helping the state of Washington do with their trial, is what is the right kind of content and flow for a user who's receiving this notification. The verification server, the reason that a verification server is in there is simply that to protect the integrity of the system, we need to make sure that we don't have people randomly reporting themselves as positive. We don't want false positive reports. You can imagine, teenagers or other malicious actors running around and being in contact with as many people as they can, and then reporting themselves as positive and essentially polluting the data that's up on the national key server. If we had a bunch of false reports on the national key server, it would really undermine the integrity of the whole system. So the idea of the verification server is simply that before you can upload or report yourself as positive, you must first get a confirmation code from the state public health authority. And the confirmation code right now, the Google designed server is an 8-digit number. You can think of it as an 8-digit PIN code. And basically, you'll get that code because somebody from the state will call you or text you and say, okay, I say state, but it could be a diagnostic laboratory or some other actor authorized by the state public health authority will contact you and offer a report that, okay, your test is positive, provide normal guidance on what to do now, what sort of health appointments you should take, what sort of self-care you should exhibit, what sort of, the fact that you should isolate yourself. But it also offer you a PIN code that will give you when you type that PIN code in, it doesn't immediately upload your status. It simply unlocks your device's ability to report yourself as positive. The verification server can be hosted by individual states. So for example, the North Dakota solution is going to go live with a verification server that was created by the developer who created the North Dakota application. Because most states don't have the expertise or agility to quickly create their own verification server, Google is going to be working with APHL to host a verification server, a multi-tenant verification server that many different states can share. And those details are still kind of being worked out, but the ultimate value in doing that is just to reduce the kind of the technical and hosting burden on each of the states. This is the architecture that we're, a very stylized architecture that we're building with APHL. A huge part of what Microsoft's doing for APHL is simply helping them figure out how to build a really resilient system that can be used by tens, if not hundreds of millions of users every day. So we're dealing with issues like, how do we make sure that the data is protected, that the system's fully secure, that it can scale to support tens of millions of apps downloading key data every day. Exactly how much we need to scale is actually a subject of debate and lots of swags. Because we just don't know how many people within the US are going to participate in the solution. I personally believe it'll be relatively small at first, but probably grow over time as people gain confidence in the solution. There are a couple of technical specifics in here, such as GitLab and Rancher. APHL is a very competent has a very competent engineering team that's especially experienced with AWS. They have a number of Kubernetes clusters that they're running inside of AWS, and they use a third-party management tool called Rancher to manage those clusters. So part of what we're doing with APHL is using Rancher, or helping APHL hook up their Rancher management tools to the Azure Kubernetes service on which we're hosting the national key server. We're also using GitLab as the CI/CD pipeline to manage the kind of whole release workflow, both for internal development as well as production deployments to Azure. The applications that we're using is Google on its website has published what they call a reference server, and the reference server is literally the code that we're deploying. We're not. Our team has done a number of pull requests against the reference notification server, and most of those things are things that make the reference server play nice with Azure. As an example, we want to make sure that all of the secrets within the code, such as database connection strings and passwords, are stored in Azure Key Vault. And the Google reference application didn't have an implementation that was Azure and Key Vault aware. So our team did a pull request to address that. The Google reference server is a microservices architecture. It has, I think, 7 microservices the microservices are pretty straightforward. There's one that's a listener that listens to new keys that are being pushed by applications. There's another microservice that wakes up a few times a day and does the aggregation and creates a export file that is then becomes the file that is downloaded by all applications. The key files that are exported by the service are published and shared out through Azure's content delivery network. And although the amount of data that we get from any particular user is quite small, and to put that in perspective, I mentioned earlier that the TEK server, or the TEKs with metadata and their 16-byte random number are about 30 bytes. And we get up to 14 of those for each user. So, you can do the math on that, and it's, 400 to 500 bytes per user, plus network overhead. But when you start aggregating those things across, first of all, across hundreds of thousands or potentially millions of people reporting themselves as positive and being downloaded by tens of millions of users, you range from hundreds of terabytes per day being downloaded to dozens or hundreds of petabytes being downloaded. Well, dozens of petabytes being downloaded, hundreds of petabytes being downloaded would be like a wild success scenario, over the course of a month. But you can imagine that just when any application that has tens of millions of users downloading data can potentially have scale issues. So we're making sure that we have that scalability in place. Let's see, I can't remember. Oh, here's a overview of what these different microservices do. There is a concept of federation in this server. Federation is a pretty simple concept, but fairly complicated to implement. A big reason that APHL is hosting the national key server is to make sure that all the participating health agencies in the country are using a common key server, so that as state residents move across state lines and start exchanging keys with people in other states, any potential exposures are aggregated nationally and reported out nationally. So what that means is, I live in Washington State. If I were to go hang out with Scott Becker, who is in the DC area, for a few days, and one of us were to report ourselves as positive, even though we would have different applications, because they're going to the same key server and we're all downloading from that key server, I would get notified when if Scott's keys happen to match a key on my phone. What Federation does is that allows us to extend that to a national level. So outside of the US is the only place where Google and Apple are allowing state level exposure notification participation. Internationally, it's one app per country. Some of the countries that are live currently are Germany is probably the most prominent example. Gibraltar and Ireland are sharing an application. They're live. Some other EU countries are live. What Federation does is essentially a back-end process where key servers, for example, at some point we will likely federate with Germany once travel opens up, so that the US APHL server and the German server will essentially trade information, trade positive keys between the servers on the back end, and then make those keys available to the applications in their own countries. I think I mentioned that Microsoft has brought its best privacy and security minds and best practices to this effort. And we've gone so far as I had to provide a similar presentation to Kevin Scott, who's Microsoft's CTO, basically to satisfy his concerns about privacy and security. And we're quite, not only are we satisfied, that because we haven't identified issues, but we've been incredibly impressed with the thoroughness of Apple and Google's design. We've verified that the no PII data can be uploaded to the server. We also are taking steps to make sure that the server never stores any private data. So for example, we never store IP addresses. We also, part of the no PII, our private data, the key server does not accept any metadata. We literally reject any sort of data that's uploaded that has anything other than TEKs in it. And if any metadata comes along that's text in nature, and you can imagine text being phone numbers or email addresses or names or just some other random key value, we don't accept any of that information, and all data must be signed by the verification server, and anything that's not in the right format with the right signature, we simply toss away. There's has been some news about Google requiring you to have GPS turned on in order to use the application, but that's not the application itself doesn't actually collect any data. That's just kind of an artifact of Android's, how Android's OS architecture works. We are applying the same level of security process and operations that we apply to Microsoft's premier Azure services. And that concludes my presentation. Thanks.
Thank you, Jeff. That's a wonderful, wonderful summary, and thanks for that. Thanks for that very inspiring and kind of very thorough look at various issues. Let's do a couple of questions while our next speaker, Sam Zimmerman, sets up. I think the first obvious question would be, what if certain states go their own way? What would you keep them in the fold or treat them like a foreign object?
Yeah, it's not just a theoretical thing. We do expect one or two states, or maybe a few more, to go live with their own server. The key thing, first of all, is that what really matters for end users, or for Americans who are using this solution, is the national key server. The verification server is something that states can do, and it won't affect, on their own, and it won't affect the overall national nature of the solution. We do expect some states, I think Alabama is one example, that might go live with their own server. And what we plan to do in that case is go through the federation approach temporarily, so that we can, as part of a migration effort. And what we would do is we would essentially federate with the state for 14, 15, 16 days, so that all of the new data from that state is available on the solution, and the state would cut over and start uploading their data to the national key server. So it's okay, but we don't. I'd prefer that everybody go live on the national key server, but politics are what they are, and states sometimes need to go their own path.
I have one more question, but I want to see if any of our panelists or speakers have a thought or question here.
One really practical question, Sam Zimmerman here. The verification server rollout we're seeing is really important and tricky. And do you have a sense as to the timing of when that might be standardized?
Yeah, I don't exactly. Scott and APHL have graciously agreed to also host the verification server, and we're Google, APHL, and Microsoft have just started the conversations about how to get that done. My hope is that because there is an existing verification server code base that's open source that Google has published, so getting it up and running will not be technically challenging. It's more a matter of logistics and timing. Scott, do you have anything else you want to add to that?
Yeah, I'd say that, you know, we'll have more to say about that probably by mid-August, maybe a little bit sooner. So what we're trying to do is, while we tie up all the loose ends, the legal stuff and whatnot, you know, we're really thinking through how do we do this quickly. So, you know, stay tuned on that. It's a good point.
Thanks.
And is there, Scott, given that APHL has so much expertise on the lab side as well, and I know privacy is a concern because most lab activities have confidentiality but no privacy, because you know all of the information is stored along with the tests and in fact reported to the government. How do you see that reconciling, given that Apple Google protocol, as Jeff just said, doesn't allow any metadata?
Yeah, so actually, it's a great question, Ramesh. That's one of the reasons why we are using different servers, and we're not, you know, there's no way anything could touch each other. So, you know, we have protocols in place for that. All the PII work that we do is in one place, and then exposure notification is here, and then the test verification would be someplace else. So that's the strategy. You know, just knowing that there's no PII involved in any of this is what gives, I think, everybody great comfort. I think there's still a lot of work to do on the privacy side and convincing folks and whatnot, but we'll get there. We have to be as transparent as possible, and I think that will help the situation.
That is fantastic. That is fantastic. Are there other thoughts or comments from other panelists? I have one more question, if maybe last one, and then we'll move on to Sam Zimmerman. You made a very important comment about the metadata that will be scrubbed. But one would argue that many states would like to actually use some of the metadata, something that still, you know, still adheres to the Apple Google protocol, and use that for epidemiology. What's your thinking on that?
Well, from a technical point of view, our implementation simply doesn't support it right now. It is possible if a state were to host its own verification server that they might have some metadata that they track within the verification server. If they were to create their own, the generic verification server doesn't support it. However, the verification server works in a way that is equally anonymized. The only thing that the verification server does is sign a hash of the TEKs, so there's no way to go from from when your application connects to the verification server and says, give me permission, it's uploading this hashed value, which is hashed of the combination of all your TEKs. There's no way to get back to your actual TEK. So ultimately, even at the verification server level, the state doesn't have any personal or private data about you. So I think that the real answer from a technical point of view is that it would have to be the public health community and, you know, epidemiologists within Google and Apple to kind of at a policy political level agree on what sort of additional metadata that they might want to add to the protocol. And only once that's actually done and the protocol is updated would we have any ability to support additional metadata.
Definitely, definitely. So let's go ahead.
Pardon me. It just you know, when we talk about it's really important when we talk about data. That, you know, part of the reason why Scott and the folks at APHL that partner with Microsoft is for the end user to make sure that they feel comfortable and confident in terms of scrubbing that data and not, you know, pinpointing it back to individuals because there's a high level of sensitivity. You know, for us, a bunch of technologists on the call, we understand the power of data and how this could certainly advance to tackling the problem. But for the end individual who isn't, is generally skeptical, especially here in the United States, around partnering with governments, we want to continue to be clear in making sure that people understand their privacy and data, and that we're going to respect that as much as we possibly can. So
that's a very good point, Nate. So on that note, let's move on to our next speaker, Sam Zimmerman. And all panelists will be available as well. So please enter your questions in the Slido, sli.do, which is linked from the responsibledata.ai website. So if you just click on Slido anonymously or with your name, you can ask questions, and we will continue to ask them to the panelists as the time goes on. So Sam Zimmerman, I have gotten to know him. He has really kind of devoted his life over the last few months, helping many states and nations launch the GAIN app as well as the GAIN server, which is something that we just heard a few minutes ago. And he has a lot of insights on the server and the verification server and the key server and so on. So Sam, I know we gave you a very short slot today, so please take us through, and I'm sure we'll invite you back again to talk more.
Thanks, Ramesh. Yeah, my name Sam Zimmerman. I am a entrepreneur by species. I love building and founding technology companies, and have in the Boston area for some years. I've also been a big fan of academics and research, working in Josh Tenenbaum's lab, extending AI. So in late March, whenever my General Catalyst-backed travel insurance company fell on bad times, I took a step back and said, with my skills and abilities, what can I do to have the greatest impact around the world for communities attempting to combat, face, and reopen COVID? I wonderfully was connected into the PathCheck community, and since that time have been working nonstop with our very large community, with stories quite similar to my own, as well as dedicated technologists, politicians, and epidemiologists around the world to build contact tracing technology. My talk today is really going to be focused on some of the nitty-gritty nuances, some of the more complicating factors involved in deploying a GAIN application, verification server, ENS server, and we won't touch on it today, but even the marketing and branding, which is an incredibly important component of the successful launch. This will be kind of a brief talk. I hope later to kind of do a little more deep dive into certain topics and tutorials thereof. I think one of the major challenges that we discover is really disseminating that information so that others who are thinking through similar problems can collaborate and cooperate and understand those shared learnings. So looking forward to doing that a bit later. So the agenda for my talk, just a brief introduction about the PathCheck Foundation. The next section is going to be, Google and Apple came together to produce one protocol. The fact is they are two very big companies moving very, very quickly. And there's some really important differences to understand between the different OS implementations that bubble up all the way to the user level. So we're going to kind of do a deep dive into some of those topics there. Highlight a couple of gotchas and pitfalls. One of the not fun parts about being on the bleeding edge is that you bleed. And we've seen a lot of projects and learned a lot of things ourselves, and really want to share those learnings that we've and others who've launched initially learned, so that others can benefit as we go. We'll have a kind of brief discussion on the verification server, a really, really important piece of technology, and a really that has a lot of subtle trade-offs to think through. And so we'll talk through some of those. We'll discuss the EPI program, which is Apple and Google's term for what counts as an exposure definition, and in particular highlight how the underlying technologies are moving pretty quickly, and how a nation or state might approach doing so. Lastly, we'll have a couple of reflections on what's coming, or arguably has come, around v1.5, which is a major update to the API on Google's end, with a similar update from Apple coming. So that's, without further ado, we'll dive into a bit about the PathCheck Foundation. So we are a community that I've never seen before. It's really best described as a movement composed of 1,600 volunteers around the world, an incredibly lively and active software development and research community with over 50 plus full-time experienced technologists helping understand the problems public health authorities are facing, helping build the technology that public health authorities need, and helping integrate these technologies and deploy them successfully. We're very proud to have 8 plus jurisdictions. That the process of getting a GAIN entitlement is a bit tricky, but we assuredly have access and are working closely with 8 plus jurisdictions worldwide, representing over 50 million citizens who could have the potential to download these applications. And we've also been co-creating this with Apple and Google and other developers around the world. We've identified over 6 bugs and helped kind of triage and evolve the protocol forward. So it's been a wonderful experience and a wonderful challenge to see these really great tech companies move quickly. But we all know by moving quickly, there's going to be some rough spots. And so we've been able to kind of help round those out a bit. Really quickly, I'm just going to provide a quick high-level demo of our approach. So you hopefully all can see my screen. And you'll notice that I have a couple different PathCheck apps. These are apps that are actually being deployed. These are around the world. These are in test flight tests. So we're doing active testing with these builds. And I'll just pull up quickly. The applications are pretty lightweight. They're pretty simple. This one has an exposure history, a home screen indicating whether or not the exposure is actually live, and enables a user to report COVID-19 positive tests. Really quickly, we'll note that there's for another jurisdiction, they actually wanted an additional modular feature. They had a different use case, a different way in which they were integrating into manual contact tracing flows. And as a result, they asked for a symptom checker. And so this build that we control via build time flags has an additional exposure, has an additional symptom checker triage that can be embedded in different parts of the application. So it's our hope, by working with so many different jurisdictions around the world and building modules that are solving similar problems, we'll be able to leverage those shared learnings and shared modules for other jurisdictions around the world. Going back to my presentation, we're going to now kind of dive into the one protocol, but in fact 2 different APIs. The first thing to note is that you might anticipate that the APIs would have similar names or even have like the exact same functions. And in fact, that's not the case. This is not an exhaustive list. This is just a list that the PathCheck team has enumerated and worked through and decided kind of what and how to implement. But 4 very important components: the exposure summary, which represents kind of an aggregate view of the set of exposures; the exposure information, a more particular view about when the API is asking and checking for an exposure; the exposure configuration, the setting that determines the definition of an exposure; and the risk score, the calculation used to quantify exactly how risky epidemiologically this encounter was. And you'll notice that generally Apple provides more information, more features at times to a level of confusion. There's also somewhat arbitrary limits. So you'll see that Apple limits the total risk score, while Google, at least initially, did not. And there's some really interesting, the risk score in particular, I think has in many ways the most important conceptual difference, where the Apple score kind of allows for certain interactions to be totally excluded if they meet, if they're below certain thresholds, and to operate off of that, while the Google one doesn't necessarily encourage that operation as much, and doesn't as naturally kind of trim off those small interactions. So while it's likely not material, I think the really high level takeaway is these are being built by two different teams, and I fully expect, and as you'll see in a couple other slides as we go, I fully expect that these differences will increase in scope, not decrease in scope, as the reality that this protocol is embedded within an operating system that has been engineered in total isolation begins to be faced more materially. I think this is one of the most major pitfalls that several different applications had, and the Swiss approach is currently the predominant one. We're actually advocating for and advancing a different approach, and getting kind of cooperation from Apple and Google and buy-in thereof. But at a high level, particularly with Android, if you're if you're not careful, and you want to kind of hone in on a particular exposure, you want to check to see if an exposure happens via exposure information, that's actually going to notify the user every time it's called. Google and Apple vary in the amount of times you're allowed to do it, and they're actually changing those numbers, but it's broadly between 10 and 15 times a day that you're allowed to check for exposure information. And in the OS, it actually asks for and notifies the user on your phone every time that occurs. So if you're a user and you have 15 messages a day that there was an exposure information request, you might begin to become exhausted by the messaging. It might become a noisy application, and it also could potentially even drain the battery. Though I think that's TBD. But ultimately, by kind of using the protocol as they intended it, and using exposure information, you're gonna overwhelm your Android users. And so the Swiss solution is to really dive into the exposure summary, a wrapper around and containing broadly the exposure information to hack and draw that information out of that message, which doesn't have the same notification problem. But the issue there is that's really kind of working against the grain of the v1.1 API. And so it's not your first implementation, and it's not really how the API was designed to be worked. So it's a hack, and it's a hack to be wary of as your developers are diving in. This is a really, really important point, and this really gets beyond the API. This is really a platform level change. For iOS, the ability to participate in the exposure notification protocol required a software update. Now, iOS users traditionally trend to 80 to 90% adoption within 6 months, but in a pandemic and with the timelines we're talking about, that timeline is something you really want to consider and think about as you're looking at your populations and the breakdown of their users by iOS and Android. Android, I think, really showed well here. It does not require an OS update. If you're on 6.0 and up, they push an update via the Play Store that enables participation in the exposure notification protocol. So that's a really important difference at this time between the way in which users will gain access to this protocol, and a really important learning as you're thinking about how to communicate and market and drive adoption. This is a fascinating one, and one that we discovered, and members of the PathCheck team discovered, and we're still confirming and trying to track down. But the TEKs, as Scott was referencing earlier, in several implementations, we've checked 2 so far ourselves, and the Apturi implementation. The Android hasn't implemented a flags field as part of the actual packets that are being exchanged between phones, while on iOS, the flags have been implemented according to the protocol. It's important to qualify that this could be an error in a couple of different levels. It might not be an issue or a bug on Google's side, but at this point, that's kind of our best guess, and we're trying to track that down. Another kind of fun point of working with really fast-moving, cutting-edge technologies. I think this difference is something that's going to become much more important. Kind of when I talked earlier about how the operating systems really were built in isolation, largely in isolation. They have access. They give developers access to APIs with varying degrees of privacy. So on iOS, the developers are not given access to an API that allows the app to know what country or state the phone is in. This is done deliberately based upon Apple's privacy conditions. If you imagine if you are an American and you flew to Cuba, Apple wants to say, we're not going to allow an app to know that you in fact had gone to Cuba. While that could potentially hurt certain telecom settings or whatnot, or make it a little more complicated. Where Google actually provides an explicit API that gives the user access to the country where the mobile phone currently is. Now, this is what you would think of as a pretty small. It's a very simple API, but when you get into a roaming world where phones are where it's really important to understand the different countries a phone has been in, you really need to, it changes the nature and constraints of how you create roaming protocols, protocols that allow privacy preserving exchange of keys for tourists who entered a country or left a country, for them to get notifications about exposures they might have had at the original country, and for them to share their data in the event that they were COVID-19 positive with the countries they visited. This is just one instance. It's one that we're going to cut our teeth on pretty quickly, but there will be others to come. These will become, there will be more and more overhead to maintain parity between the Apple and Google protocol. They'll make sure that it's possible, but the amount of work involved and the amount of kind of tricks to make sure you get there, I fully anticipate will be increasing in scope. Great. So hopefully now you guys understand a couple examples of where one exceptional collaboration expresses itself very differently in different technologies. Now we're going to switch to a couple gotchas and pitfalls that we've seen from our conversations with other game developers around the world. So the first thing to highlight here, and this is a really kind of a pretty substantial and subtle implementation point. The vast majority of successful game app launches at this point don't use the iOS's own kind of built-in risk configuration scoring, and instead they roll their own. And Apple allows you to roll your own, and broadly they all look the same. The German app, the Swiss app, our approach are broadly a kind of light CDC level recommendation. Now, what's really important to notice is that on iOS, there's certain times where the OS exposure configuration settings are actually still operating on that risk model that the Swiss, German, and our apps aren't using. And so that means that there is a case, while it's not particularly likely, there is a case where a user could get an exposure notification from the operating system, according to the kind of much looser definition that's implemented there, while the definition encoded within the application might not trigger. And so it's a really important and subtle case to think through as you're kind of building those flows. Exposures and what counts as an exposure are being split between two different areas, and broadly that's fine, but it's not. It in principle leaves asymmetric exposures to be exposed. At a high level, I think this goes without saying for a project that was conceived and executed on in 8 weeks. But there's been several breaking API changes and bugs, particularly on the server, the open source server implementation. In our experience, and really an essential part of the success of all launches around the world, is deep conversations and connections with other teams, understanding what had been successful. Each app, with each launch, we learn a new strategic point about what to do or what not to do, and to iterate kind of where there's failures. Being upfront and frank about launch failures and things that could have done better have enabled our team to save immense amounts of time and energy as compared to teams that have gone before us, and I anticipate that trend will continue. At a high level, a mistake we made, if you look at the exposures, the protocol, it really appears like you're going to get kind of like a daily summary. You're going to be able to kind of have a notion of when, even at a daily cadence, and in fact, you don't. The proper lens to think to this is the user will know they had an exposure, and there will be, if you really wanted to, you could provide boundaries, but it's going to be awkward. It's not. It's really not. It's not set up to be tied to two dates in the way that we thought it was, and in way, and frankly, in which the documentation thought it was. And so that calendar view, we actually pushed an update. I didn't update my phone. That updated updated that screen in light of those learnings. So that's one of the things that we got our way around, and that we don't want other teams to have to be concerned about. Another kind of high level pitfall, and I think we're going to pay for this much more in the coming weeks, is as we have more versions of the API with pretty substantial changes. We went from 1.0 to 1.1 to 1.5 in a matter of months. So that fully anticipate your server is going to need to deal with different exposure configurations based upon the operating system, particularly on iOS. And in turn, there's going to be different kind of interpretation limitations thereof. It's going to be, you're going to need to think about the operating system, think about the device, and think about the exposure configurations that need to be maintained. So keep an eye out for that. I think we see it entailed by the architecture, and it'll be something we need to kind of be thoughtful about as we go. The last thing, I'm really proud of the worldwide response to this. I think Google and Apple creating the tools and infrastructure, given their market share, and allowing open source communities to develop and build the applications, and to support the launch of public health authorities. It's a beautiful thing to see. I think that what we've done several times with other apps, with other open source projects that have similar parts of code or similar code snippets, the previous things I talked about around those differences between operating systems entail that each open source project made really particular decisions about how to handle those edge cases and gotchas and bugs, and how well they're thinking about kind of these substantial updates. And so whenever you're thinking about an open source project, really understand that they're not all created equal due to the changes that we have now. So I think we're happy to talk through that. We've looked forward to and really appreciated learnings and sharings and collaboration with other groups, and really encourage other groups who are doing so to approach it the same way. Great. So now we're going to switch to the verification server. This, as the previous talk highlighted, is a server that's responsible for tying a COVID-19 positive test to an individual using a phone via a verification code. As also was alluded to, the reference implementation by Google is very, very strong, and is frankly pretty well set up for v1.5 API changes. The most kind of important thing, in my opinion, that really gets underlooked is, in order for this to be successful epidemiologically, so you can solve the adoption problem, you can have tons of people using your app, but if you don't have it actually closing the loop and closing the loop thoughtfully on the verification server, the actual efficacy of the tool is deeply, deeply challenged. And it's really hairy, it's really complicated. I think I'll get a bit later, we'll kind of walk through I guess the primary trade-off here really is there's a push to get that verification code to the user as soon as the test result happens. So you want to write an automated script that's going to enable you to communicate these verification codes to potential app users as soon as possible. That's really great because it enables users to potentially self-quarantine and reduce the spread during a very high-risk time. But on the other side, there's been consistent findings across launches that you get better engagement with the application and better engagement with individuals completing that verification code upload if you have higher engagement, if there's actually someone calling and talking to the person and explaining the app and that they're the privacy concerns thereof. So it's really, really tricky to develop an implementation that is fast and automated and getting at the cutting edge of that curve, but also has that high touch human element that's necessary for people who are willing to donate their keys in order for this protocol to work. We've found, importantly, that around the world, and particularly in the US, manual contact tracers initiatives have been scaled immensely. If you imagine an organization and you, in some cases, 50x your organization over the course of a couple months, and in most of these cases with 5 or 6 other technology initiatives at play, including switching out your case management program, updating your analytics, constantly updating scripts, with a workforce that might have been only on the job for a couple weeks, and that was curated over the course of an interview process that's much shorter than normal. We're seeing across the board that integrating thoughtfully into manual contact tracing flows is a really, really subtle challenge, and one that you need to have a lot of really important discovery and understanding of how these systems are being implemented around the world in order to create a solution that is likely to be successful, that the manual contact tracers will understand, and that is low touch, not adding a lot of extra effort or work to their already really demanding IT teams and individual caseloads. The verification server also has, embedding this verification server in a manual contact tracing flow has the ability to gather additional information. You can ask whether a user had gotten an exposure notification during their contact tracing interview, or you could ask whether they had uploaded those COVID-19 positive keys. So by getting that information about what the user's app experience was and tying it to a case in the event where the user is comfortable and consents, we're able to refine and iterate on the FB program in a lot more intuitive manner. And that's something we're building for and launching with in the jurisdictions we talked about. A gotcha here, and I think this is a very subtle issue. I think that I'm highlighting predominantly the PR and privacy branding risk here. Firebase has been in the news. New York Times article, a couple of papers came out because it's telemetry and location information being kind of not of the same standard as this protocol. And so I think that Firebase is an exceptional identity management tool with a lot of potential configurations, but it is a risk. And I anticipate, like, there's been papers and launches already highlighting that using Firebase is, even though it's only for the manual contact tracers and not for the app broadly, it's just that it's a word that adds PR and branding risk, and that we would all want to be thoughtful about in creating our solutions to limit as much as possible when thinking through the real and serious risks to marketing and adoption. I think it's totally unfair, but it's the name of the game. Lastly, I think this verification server is incredibly dynamic. It's by among the EN server microservices, it is comfortably the most dynamic and comfortably the most brittle. So as we're thinking about, expanding from GCP, where it is most naturally deployed, to AWS and Azure, this is going to be, moving something that is changing at the same time, and fully anticipate that you're going to be needing to invest in consistent maintenance of the higher level architecture. The two other learnings, I skipped through them. Identity management is essential to understand early, and so we encourage people who are talking about and thinking about how it's going to impact what users are going to be sending these codes to understand what their identity management constraints, because no one wants another login. And lastly, these manual contact tracer organizations are very diffuse. We in many cases have prime minister level, VP, like the vice president's office, the governor's office, like sitting down and focused on making sure something works. But these systems are diffuse and local in nature. And so it's really important to think bottoms up as well as top down in making sure your solution is going to be adopted. Great. I think I'm up on time, so I'll move quickly through these next two topics.
And if you want to skip over AP and talk about the V1.5,
happily. Yeah, so V1.5 is a major API change coming by Google. We don't know. 13.x is what Apple has called it. We've seen some sketches thereof. These are some really important changes. There's the infectiousness, which allows for whenever the onset of symptoms started, which is important in understanding the nature of the risk of an exposure. That's supported in our implementation of the verification server and will be very powerful going forward. There's a much stronger risk scoring more broadly. It's a lot more standardized. There is some kind of poor naming, I would say, that they call it a negative test, report a negative test result. It's actually just a test revoking. For us who kind of think a lot about this stuff, a negative test and a revoked test are not the same thing, and managing those risks are a bit different. So I'm still pushing them to change that. There's been major updates in terms of calibration. The devices are quite subtle and complicated, and Google in particular, with their many different devices, went through a really under the hood push that's not very public, that created a lot more calibrated results, enabling a lot better understanding of the risk. There's a lot better daily summaries to be exposed to users, so expect apps to become a lot more intuitive and a lot more informative. The notification Mageddon that the German and Swiss teams had and that our solution gets around as well is going to go away with this exposure window concept, replacing the exposure summary and exposure notification concept. Importantly, to flag, federation, as was talked about earlier, is very, very important. But there's the Google open source server is not yet V1.5 ready. The Google team and our team are working really closely to get to that state. But launching an OS server, Google OS server, in a federated manner is still TBD. We're working as quickly as possible. And lastly, as a result of this understanding of infectiousness, the verification server might start collecting additional data, like the onset of symptoms, which when parlayed to the ENS server has a little more tighter coupling, at least at the domain model level, and something to consider. Well, with that, and a bit over time, thanks much. Really appreciate the PathCheck community. Much of the results I've shared are a result of our great team working around the clock to create and share these learnings. And a reminder that we are here to help PHA's launch, and we'd love to talk with you about our learnings and whether we could be helpful. Thanks much.
So Sam, maybe I'll put you on the spot here and ask the same question that I asked Jeff, which is, given that you're in 8+, you have entitlements in 8+ jurisdictions in various US states and also worldwide, and all this amazing plan you showed that would require, for example, one of the apps you showed require collection of non-PII, but still epidemiologically useful information about the age groups or other things like that, would you go with, Microsoft National Server, and what would you need, or would you treat that only in the second iteration of your relationship with the states?
It's a really great question. I think if I'm being frank, I think that, a major reason why zip code is added is so that the user can get specific testing information and not their whole state or country's testing center. And so as I think about the apps being usable, as I think about being both the end users and the PHAs, I think that limiting metadata is going to materially impact the success of these programs. And I anticipate, based on conversations with our jurisdictions who are so focused on adoption, that could be a gating item.
I appreciate the honest answer. Does somebody from Scott or Jeff or Nate want to kind of answer that? I'm sure we'll set up a longer conversation between this team as time goes on.
Yeah, I think that's right. I think we do need to. It's a great point, and I think as we get more deeply involved to hear what some of the issues are, there may be ways that we can help mitigate that. You made some really great points. I also think that not knowing the full audience on this webinar, but the public health community could also hear some of the lessons learned that are actually going on, and ways to mitigate some of the challenges is really important.
Other questions from the panelists?
Hi, Sam. This is Lognajita. It's a informative talk, but I have one question. So you hinted on several times that adoption level is really important. And how do you see the application working when the adoption level is low? And I'm especially concerned about the risk score that will be generated. How does that relate to the low adoption level? Any comments on that?
Given what we have seen in Europe, for example, the adoption has been low.
Yeah, I think Switzerland is stuck, to use a phrase from their team, stuck at 15% due to, and it's not appearing to move upward. So you get one launch to nail that high adoption push. I do think that the original study that was published really thought of apps in isolation, independent of a lot of other major health initiatives like wearing masks. And we do think that there is additional value by having 15% of the population have the apps. But it's far from where it would need to be to materially impact that folks care about. Not to go on a different topic, but we do anticipate, Apple and Google have stated that the protocol will go at an operating system level, which will change the adoption game. And that's it's a big topic and one we can maybe explore at another time.
Got it. Thank you.
Sam, one more final question and then we'll move on. So I know your team is probably a world leader in thinking about the V1.5 and what could be coming in V1.6. And we just heard from Jeff earlier about how they are thinking about it. I mean, are you expecting some stabilization, or you think this is innovation and we will continue to bleed on this bleeding edge?
It's a great question. I do think that the name of the game is staying right off the bleeding edge while very close to what's functional. So find stability, find that, and to be clear, I don't think stability is at 1.1 given several of the issues. I think stability is most likely to occur at 1.5, at which point then consistent and thoughtful updates across the different parts of this technology stack will be required. But I think stability is going to come at 1.5 and not before.
Scott, Nate, or Jeff, any final thoughts?
Yeah, so again, thanks for the opportunity to contribute to this. It's a great dialogue. I look forward to hearing more. I just want folks to also recognize how incredibly stressed governmental public health is in the US. So I'm sure Sam knows that with his team working directly with state governments and health officials. It is incredibly taxing. It's taxing for all of us, but these folks have been on the front lines since January. So bear with us. We have a lot of the same. We all have the same goal. So we'll work together. We'll bring some innovation through this pandemic. And there's a lot of good a lot of good things that can come out of exposure notification beyond COVID. I think of things like we work in the global sphere as well. I think of TB and exposures for other kinds of issues. So keep at it. Thank you all for what you're doing. We appreciate it.
Definitely. And MIT has played a role. We'll hear two more speakers from MIT and NIST, and MIT has played a role from World Wide Web Consortium to Auto ID Center to all kinds of server protocols. And I'm just very happy to use this platform to bring some of the smartest minds to come together. I'm totally with Scott here that we'll continue to have issues, but as long as we work together, we can make it happen. So very soon you'll hear about some more coordination efforts that are coming up, especially under Frank Moss and David Kong, as they work with the government as well. So let me hand it over. Thank you, Sam. Let me hand it over to Gary Hutke, who, again, one of the leaders in thinking about what it means to use the Bluetooth signals. So I'll hand it over to Gary, and after that we'll hear from Doug and Omid on the NIST challenge that you definitely do not want to miss on how all these pieces of the puzzle are going to come together. And we'll have a much more detailed conversation in coming days. But think of today's sessions as teasers to see how various teams are working together to bring these solutions to fruition. So handing over to Gary.
Sorry, I had to unmute myself and I was covering up my screen. Thank you very much for inviting me. My name again is Gary Hatke. I work at MIT Lincoln Laboratory. So for those who aren't familiar, Lincoln Laboratory is the Department of Defense laboratory that MIT operates. But early on, we were asked to help in the PACT program, which was put together on campus at MIT. Some of us from Lincoln were asked to help in developing some understanding of how well this Bluetooth Low Energy, or BLE, technique could possibly work to determine whether or not people were actually too close. Because after all, this is contact tracing and close contact tracing. The idea is, can I get these Bluetooth signals to allow me, through whatever means possible, to measure whether I'm in close proximity? So we've taken a pretty careful look at that. Modulo the type of data that we collect during a pandemic, when it was highly encouraged not to go into the lab, as well as to not get within 6 feet of another person. So the data collections that were done were oftentimes in people's houses. But we still attempted to do a fairly rigorous type of data collection that would allow us to make some reasonable conclusions as to how well these things could work. So the PACT program at MIT is basically a full-up soup to nuts concept where you're talking about understanding the contact detection, going and analyzing the privacy of exposure notification and all of the things that have been covered earlier today, as well as what sort of action should be taken if a person contacts a test positive case. How should that be handled by public health? I am going to be talking primarily about the Bluetooth low energy detection phenomenology, because if that doesn't work, the rest of the system is basically trying to work on bad data. So how does Bluetooth low energy sense whether or not a contact is too near. So this has been somewhat described already, but I'll go over it once more. Your phone is constantly, if it's enabled with this API, it's constantly transmitting Bluetooth low energy chirps. And in addition to having the encoded number that we heard about earlier today, those chirps also have the transmit power with which they were sent out of the phone. And it was hinted as to the calibration problems that Google was going through, given that Google operating systems occur on a number of different hardware platforms, as opposed to Apple, which controls their hardware platform independently. So understanding actually how much transmit power is getting out of the phone so that you can encode that into the chirp requires a certain amount of calibration. On the receive side, so this would be a potential contact, they're going to measure the received signal power that they get from any of these chirps that they receive. And that's going to be quantized in what they call an RSSI score. And that's measured in dB milliwatts of power. So as you receive the chirp, you not only demodulate the information in the chirp, but you also make an estimate as to the power level that you received the chirp at. And if you know what the transmit power that the chirp was sent was, you can then estimate the attenuation that that chirp encountered as it was going from the transmit phone to the receive phone. That attenuation can then be used to infer what the range between the two phones were. But it turns out that mapping attenuation to range is a challenging problem. If it was two antennas all by themselves in an anechoic chamber, and I had highly calibrated antennas and I knew what their orientations were with respect to one another, then it wouldn't have been much of a problem. But these are antennas that are embedded in cell phones, and the cell phones are being carried by humans, and the humans don't always carry the cell phones the same way. So that mapping problem now becomes much more difficult. So what are the challenges? Well, one of the first challenges is that your body is a big bag of water, and Bluetooth low energy occurs at a frequency that's referred to as the ISM band, but it's around 2.4 gigahertz. Now, other things that occur at 2.4 gigahertz are your microwave ovens at home. And all of you recognize that if you put a jar of water in a microwave oven, the water will heat up. And that's because water does a remarkably good job of attenuating and absorbing radiation at 2.4 gigahertz. So your body acts as a big absorber. And in fact, if you've got a phone up close to your body, the way the signal propagates to the other direction of your body is by actually refracting around your body. So there's a lot of loss on the other side of a person if the phone is up close to a person. So that would be indicated by the case here where I have a phone in someone's front pant pocket. You're not going to see much signal in the aft quarter of that person. And in fact, the overall signal power is going to be less than if the signal was held far away from your body, because putting that phone up close to your body effectively ruins the antenna pattern. You've got a lot of coupling between that antenna, which was designed to operate in the absence of a body, and your body, and it sort of ruins the efficiency of the antenna. So you get better propagation if you hold the phone away from you, and you get better propagation if your body isn't between you and the direction that you're trying to propagate to. In addition, if you're standing inside, there are these big reflective objects that you can come into close proximity to, and that's referred to as multipath scattering. And the problem with multipath scattering is that if the scattering appears to be out of phase at the receive antenna, the other phone, it can actually appear that you have less signal power than you actually do. That's referred to as a multipath fade. And these multipath fades can be highly varying depending on small motions of the phone. So you've got these big effects due to body attenuation, and then you've got sometimes as big effects due to multipath fading that can all make that attempt at mapping from attenuation to distance much more difficult. And in fact, it ends up looking sort of like a stochastic process. So the amount of signal power that you receive is in some sense random. Random, but at some range, you just don't close the link. The phone stops being able to demodulate the chirp at all. And so there's a sort of range of ranges for which a phone can receive the chirp, but you're not necessarily too close. And what you'd like to do is come up with some detection strategy that precludes you declaring an alarm if the phone is in that red area, which is too far to be declared as a close detection, but not so far away that you don't see the chirp. But it does declare detections if the person is within that green area, and that green area circle size is, set by the CDC right now as 6 feet, but who knows, in the future it could be changed to 8 or it could be reduced. So you want a detector that can be tuned to whatever the definition of that circle size is. Now, one of the measures, the principal measure of goodness for a detector is the false discovery rate. And that's the ratio of the number of false detections, so detections that really weren't too close, to the overall number of detections. So if your false discovery rate is 1, that means that every detection that you're getting was really a false detection. And it's difficult to build a detector that has a false discovery rate of 1, but it's actually not difficult to build a detector with a false discovery rate of 90%, for instance, which would say that 90% of all declared too close contacts really weren't too close. So the objective is to build a detector that has a relatively low false discovery rate while having a relatively high probability of detecting a contact that was within that 6-foot radius of the index case. So we've developed a proximity, we had to collect data in order to determine whether or not we could build a detector that could discriminate between too close and too far away. And in about 2 weeks, we had an app running that's actually was made available on test flight that would record the RSSI values that were observed by an Apple iPhone. So we developed this app and we put together a script for data collection that Doug will probably mention in his talk, that allowed us to collect data in our homes within family members, where we would have people at ranges that were within 6 feet and ranges that were in excess of 6 feet, over all sorts of pose angles between the people carrying the phones and with different phone carriage characteristics. So phones in your hand, phones in your pockets, phones in your pants pockets. And we categorized the attenuations that we saw in all of those cases. So this gives you on the left-hand side, you can see how some of this data was collected. That's one of my colleagues, and what you're seeing pictured is actually her daughter doing a collection, and you see a tape measure running between them so that they accurately know the distance between the phones. And we would actually have people spin around and collect data at different pose angles with different phone carriage statistics. And then we would collect all that data and analyze it. So on the right, what you see is the received power as a function of the distance between the two phones. And you can see a general trend. At shorter ranges, you see higher received powers. At longer ranges, you see less received power. But you also notice that there's a huge spread in those power levels. So that spread can be 30 dB. And if you just follow basic physics, it says if I double my distance, I should increase the attenuation by 6 dB in free space, direct line of sight. So that amount of variation dwarfs the actual signal present when you increase the distance between phones. So that poses a very difficult detection problem. So we took that data, and being statistical signal processing people, the first thing we tried to do was turn it into a probability density function or a cumulative density function. And what I'm showing you here is some of the probability density functions. In this particular case, I've got two different phone carriage scenarios. One where the phones are being held in the hand, and those are indicated by the solid lines. And the other one is where the phones are in pants pockets. And the first thing that jumps out at you is that the received signal power for the too close case, when the phone is in your hand, is much higher than the received signal power when the phone is in your pants pocket. There's about a 10 dB difference, more than a 10 dB difference. The other thing that you notice is that if I'm carrying the phone in my hand and I'm too far away, that's actually a stronger signal than if the phone was in my pants pocket and I was too close. So setting a single threshold to try to differentiate between too close and not too close, that's independent of how your phone is being carried on your person, is going to be extremely difficult. I can't necessarily set a good threshold that will work both in a phone in the hands versus phone in a pants pocket scenario. Now, the distributions I show here are exactly how those distributions were calculated, because it's not just at one range. The too close range is anything inside 6 feet. The too far range is anything outside, I think it was 8 feet, that we used out to about 30 feet. So you actually have to do an integral with some density function. And the density function, it turns out, is a little bit interesting, because that's what's the likelihood of a person being that far away from you. And we'll get into that a little bit later when we talk about false discovery rate. So what type of detectors can you build? It turns out that there's a huge body of knowledge on how to build detectors when you're trying to solve a binary hypothesis test. And you can go back to things like Bayesian detectors, and you can, there's a whole litany of detector theory that you can draw upon, but most of them boil down to something called the likelihood ratio, which ends up being, you calculate the likelihood that the phone was in one class, either too close or too far away, divided by the other class. And that likelihood ratio ends up boiling down to taking the input data, putting it through a nonlinearity, and then summing it up. So one often used way of implementing one of those detectors is don't put it through any nonlinearity at all. Just average all of the data that you collect. And the data that we collect in this case would be the individual attenuation estimates during that too long period. So the assumption is that I'm going to get multiple estimates of that attenuation during that too long period. And now I have to figure out how to decide whether or not I'm too close or not during that too long period. So I could average all of that data together. And under some conditions, which I won't get into here, but if somebody really cares about it, you can contact me later. That can be a great detector, but it tends to have issues when you're in large signal fading environments, which we find that we're in this particular case. So then there are two other detectors that you can look at. One is just looking at the minimum attenuation seen over all of those measurements during that too long period and thresholding that. So that gives reasonable performance when the number of chirps that you see is small. It turns out that this can be a close to optimal detector under those conditions. And it is robust to large signal fades because if the signal faded out, that's not going to be the minimum attenuation. You know, anytime the signal is in a fade, that's going to be one of the larger attenuation values. So you'll discount that. A potentially better solution is to count how many times that attenuation is less than some threshold and compare that count itself to a threshold. And this is referred to as an M of N detector. And these types of detectors have been used in radar for years. They're very close to optimal detectors, even in scenarios where you wouldn't expect them to perform well. And there are certain classes of distributions for where M of N detectors can be shown to be optimal. An interesting point is that this 1 of N detector is a subset of M of N detectors. So an M of N detector is always going to be at least as good as a 1 of N detector, and it's going to have the same properties. It's going to be robust to these large signal fades because that data is going to be pretty much ignored. So we're going to be concentrating on looking at these bottom two types of detectors. So based on all that data that we collected, we could predict performance assuming that we had different numbers of observed attenuation values. So what I'm showing here is cases where I've had 6 observations, 12, 24, and 48. Now, the baseline Google Apple exposure notification app is likely to only get you about 6 of these notifications. So that 1 of 6 curve is what certainly version 1.0 and potentially version 1.5 will get you in terms of probability of false alarm, which is the x-axis, and in this case, probability of miss. So this is 1 minus probability of detection. So if I wanted a probability of detection of, say, 70%, that would correspond to the 30% probability of miss. And if I read over to that baseline Google gain curve, that says my probability of false alarm with a probability of detection of 70% in this particular case, where both phones are in shirt pockets, would be about 10%, which doesn't sound so bad. But that's if I'm able to set my threshold specifically for that phone carriage case where the phones are in shirt pockets. Now, if I am able to use an M of N detector, you can see that for that N value being 6, there's not a whole lot of difference in those curves until I get to very, very low false alarm rates. So what that says is that the optimal detector, the optimal M of N detector, is setting M equal to 1 when N is such a small number. But you get decidedly better performance as N gets larger because you're making a more informed decision. So having seen that baseline detector, and it becomes obvious that as I increase N, the performance of my detector gets better. If I go back to that previous slide, things that are low and to the left are better performing than things that are high and to the right. That dashed black line is a coin flip. So that's the performance that I would have gotten if I had no information in my test at all. So clearly, if I have more samples, I do better. But if I can get conditional performance, so I can set my thresholds differently if my phone is in my pants pocket versus if the phone is in my hand, that's going to give me better performance as well. And if I can get enough observations, being able to implement something like an M of N detector is also going to give me some benefit. So let's go back. I had mentioned earlier that what we really care about is this, not only the probability that I actually detect guys that are truly too close, but I don't want to be generating a large number of false detections for a bunch of reasons, not the least of which, if the app ends up alarming you too often that people were within close proximity of you when they really weren't, people are going to start doing things like, you know, basically taking the app off their phone. So this false discovery rate is, again, sort of an integral where I take the contact density, which is how dense are these people likely to be around me. And it turns out if you assume that the people are going to be sort of uniformly distributed around you in some two-dimensional space, which is what you might expect at a large outdoor event or in a cocktail party or something like that, that means that the density of contacts increases linearly as the distance away from you increases. So you can take whatever contact density you want to hypothesize, and that's the one that I hypothesized in all these curves, and multiply that by the probability of false alarm at that range. And that gives you the number of false contacts. And you can do the same thing for the probability of detection, and that gives you the true contacts, and then you can take that ratio. So how does that translate to, based on our data collection, how do we expect that baseline Google, Apple exposure notification app to work? So, and this is assuming that I've got the phones calibrated properly. If the phones aren't calibrated properly, all bets are off. But let's say I wanted a probability of detection of 33%. So if I had 3 people that were too close to me for too long, I would pick up one of them. So that's not a great probability of detection. But if I set my probability of detection to be at that level, I'll end up only detecting about 1 person that really wasn't too close to me for every 1 person that I detect that was too close to me. And that sort of false discovery rate is one that, you know, public health might be willing to accept. If, on the other hand, I decide that I want to be able to detect at least 2/3 of the people that are too close to me, then the performance of that baseline detector, you start seeing issues, because the false discovery rate at a probability of detection that's equal to 67% ends up being larger than 90%. That means that over 90% of all the detections that I declare really weren't too close. And that can potentially overload any sort of manual, you know, we talked about the hands-on effect for contact tracing. Well, now I'm going to be driving those manual contact tracers crazy, because they're going to be following up on lots and lots of contacts that really weren't threats. And people might just decide to take the app off their phone because it's causing them to be alarmed when they really didn't need to be alarmed. So we'd like to get out of that scenario. Now, if we augmented that baseline detector with a couple of different things. So the first thing is, instead of just taking one sample every time the Google Apple app turns on the receiver to receive signals from the other devices that are chirping. And by the way, the baseline scenario is the protocol is only going to force the phone to search for these BLE signals once every 5 minutes. You might search more often than that if your phone comes out of hibernation. So if it wakes up, you can get opportunistic scans, but the guaranteed scan rate is only once every 5 minutes. So that sort of limits the number of samples that you're allowed to take, but they'll typically scan for 4 seconds. So within 4 seconds, these phones are chirping about 4 times a second. So you can get multiple chirps from each phone. And getting those multiple chirps within one scan period can be helpful. We've analyzed how much that helps. So if I couple that with knowing what the status of the phone carriage was, is it in your hand? Is it in your pocket? And we believe that we can get some sort of estimation of that by using things like proximity sensors and light sensors on your phone. If we couple all of that into the API, we can now get to a case where we detect 2/3 of the people and still have a false discovery rate of about 50%, which means that if I detect 2, I'll also falsely detect 2. So the summary of our results basically stated here. It's going to be difficult to take the baseline API and get a really good probability of detection without getting a very high false discovery rate. If you're willing to accept a probability of detection of somewhere between 25% and 30%, you can probably keep the number of false alarms down to the point where public health and the public at large aren't going to be frustrated with the app. But if you want to do better, you're going to have to start thinking about ways of augmenting the basic Bluetooth low energy detection strategy that was built in to that 1.0 app and even into the 1.5 app. So with that, I'll take any questions.
Yes, great. Thanks for your great talk, Gary. So does the panel member, anyone has questions?
Hi, Gary, I have one for you. So I was wondering, you mentioned phone calibration is required. What kind of calibration are we talking about for a proper signal strength?
So what I have heard occurs is people will put phones, and when I say people, phone manufacturers or Google or Apple will put phones in anechoic chambers and literally measure the received power with instrumentation equipment to determine how much power is actually being emitted from the phone in different pose angles, given the amount of power that the phone thinks it's putting into the antennas. So it's a fairly standard technique in an anechoic chamber, but it's not something that you could do at home.
Okay. And one simple question was, is there a relation between the how much charge the phone has with the Bluetooth signal that goes out?
Hopefully you've got power regulators within the phone that I think you'd have to get, your phone would shut itself down before that became an issue.
Got it. Okay. Thank you.
Yes, great. Thanks, Gary, once again. Now I would like to invite upon our other speakers, Doug from MIT Lincoln Lab, and Omid from NIST. Thanks. It's over to you, Doug and Omid.
Okay, Omid will load up the slides here. While he's doing that, let me just say that I'm Doug Reynolds from MIT Senior Staff, MIT Lincoln Laboratory. And this talk is with my colleague Omid Sajadi from NIST. He'll describe his position that's there. And just in the context of this, we were part of the pact. Our main goal was to try to say, can we set up evaluation to take what you heard from Gary, but then open it up for a wider set, applying signal processing approaches and known things that work from radar are great. That gave us the baseline. We wanted to know what could happen better if we set up a challenge to open this up for machine learning people around the world. To do this, we figured we had to do effective use of data sets. That means taking these data sets that are being collected by different organizations to address this too close for too long detection problem, aggregating them in one location. So we've set up a central website that has a repository of data that's not only including the data set that Gary described, other ones have been collected by MITRE and APL and other organizations around. We call the Coalition of the Willing Data Collectors. Put it in one place so people can go to that and gather it, but also creating an open research challenge or evaluation to explore new techniques and measure state-of-the-art performance. So provide a common, comparable platform that we can then compare results. People can come in there with their best ideas and be able to do those. So the website that you see there is showing the pieces, the data set and the eval. Okay, and then what makes up an evaluation? Just for those not familiar, and a challenge or evaluation, I'll use those terms interchangeably, is we need three main elements before we can unleash the machine learning crowd or the people on this to apply their magic. The first is we have to be pretty clear about the task. What is it we want to do? What are the inputs and what do we want as outputs? We need to have a metric to measure how well it's working. How well are we producing the outputs that we expect? In this case, as you'll hear Omid describe later, the proximity, being too close, or and we're taking time out for the first part. And then most importantly is the data set itself. We need to have the data to drive this. This is data-driven evaluations. Theory can take us so far, but we know real world it's going to be different based on all the variables that Gary described. We need to have this data that reflects realistic conditions so we can then use it to learn, tune, and test and see how well we're performing. The main bottom line with having a challenge or evaluation is that it creates a common framework that allows researchers to compare results, so you don't have your own experimental protocol that everyone has to unpack and figure out what was done, and to, more importantly, to build on each other's successes. If we have a common framework, someone tries some idea, someone else hears that it works, they can incorporate it and keep going. Next slide. Just to set the context on this, we've been calling this a pilot evaluation for this first run that, as Omid will go through, using early controlled data sets, the ones that were available at the time. The aims of the current evaluation are to explore the promising new ideas. How much better can we do given the data than just the straight signal processing approaches? Are there some more modern machine learning neural network approaches? We want to measure the best possible performance of that. This doesn't necessarily mean it's the one that's available in the app now, but really to analyze the conditions and inform future BLE measurement protocols. So this may not affect the current API that's out there, but if you think about the API that Google and Apple put out, it's really a collection platform. They don't make the decisions. They collect the Bluetooth or other signals, they hand it up to the app then has to apply thresholds and make the decision. They're not the decision makers. We're looking at saying what other algorithms can be applied with this and what other measurements might need to be collected in future protocols. And more importantly, we'd like to use this to refine the task, the metrics, and the data and design for future evaluation so we can make this more relevant as this rolls forward in the future. Omid will go through next on all the pieces, and I'll just mention that we do plan on having a workshop that'll happen in August from this evaluation that'll be open where people can hear about the results, give inputs, help us drive the next things on that. So with that, I'll hand it over to Omid, who will then go into the details of describing our pilot evaluation.
Okay, thank you very much, Doug. I would like to first thank MIT and UC Berkeley, specifically Ramesh and Don, for putting this together, allowing everyone to come in and present and share ideas. So my name is Omid Sajjadi, and I work at the National Institute of Standards and Technology, and I'm very delighted to share with you an overview of the NIST pilot Too Close for Too Long challenge. This is obviously a joint effort with my colleagues at NIST as well as MIT Lincoln Laboratory listed on this slide. So before I start my presentation, let me first start by sharing some background about who we are and what we do and how we got involved in this effort. So I'm with the Information Access Division within the Information Technology Laboratory here at NIST, and IAD provides measurements and standards to help advance technologies related to information access. It also, as a neutral and unbiased entity, runs machine learning and AI evaluations. And it started running AI evaluations since late 80s to help advance technologies such as automatic speech recognition, search engines, information retrieval, face recognition, and so on and so forth. And to do this, the IAD has used a model we call it evaluation-driven research and development. Here on this slide, you can see a diagram of the flow of such model, where NIST, again, as a neutral and unbiased entity, brings together researchers and technology developers together by setting up a common evaluation that consists of well-defined tasks, metrics, and data sets. And it also provides a way for measuring the performance. And the researchers who are at the core of this model, they process the data locally, and they provide their output to NIST, and NIST scores their output and sends them back feedback. And this process is followed up by a post-evaluation workshop where in which NIST presents an analysis and results of the evaluation, and researchers can easily compare and contrast their approaches to other researchers' techniques. And then the next evaluation is planned based on the feedback that we receive from the participants during the workshop. So for some of the evaluations that we run here at NIST, we are collaborating closely with MIT Lincoln Labs. And given the current health crisis and the COVID-19 pandemic, and the attempts to develop robust technologies that are effective and efficient for automatic exposure notification, we were asked to set up an evaluation to help advance the proximity detection technology using Bluetooth Low Energy, which, to the best of our knowledge, remains the largest engineering problem for automatic exposure notification to this day. Okay. So with that introduction, here is the outline for my talk. I will start by describing the objectives of this challenge, defining the tasks. Then I'll provide an overview of the data sets we created for this challenge, define the metrics, give a summary of the participation statistics so far, and a perspective on the future evaluations. So in terms of the objectives of this evaluation, again, we use our evaluation-driven research model to help advance. Our hope is to help advance the Bluetooth Low Energy-based proximity detection. We provide a common test bed, including tasks, well-defined tasks, data, and metrics to explore promising new ideas in proximity detection. And we support the research community throughout this challenge. And we help them to develop advanced technology in incorporating these new ideas. And once the technology is mature enough, we, at the end of the challenge, we would like to have a measure and understanding of the performance of the state-of-the-art proximity detection systems. In terms of the task, even though the original theme of this evaluation, this challenge was too close for too long detection, we decided to just for this pilot evaluation go with the proximity detection, which is the too close detection aspect, and we dropped the too long detection aspect. So the given this task that I'm going to define is mostly focuses on the proximity detection problem, and the task is given a sequence of Bluetooth chirps as well as phone motion sensor data between a pair of phones. We would like to have an estimate of the distance between the two phones. Now, this is a detection problem. It can be posed as a two-class hypothesis testing problem, as we saw in the previous presentation, where we define two hypotheses, a null hypothesis and an alternative hypothesis based on a threshold that is applied on the ground truth as well as the estimated distances. Here, D denotes the true distance, D prime denotes the estimated distance, which is produced by the system, and capital D is a configurable threshold, which is determined typically by the public health authority. In terms of our evaluation conditions, we have a training condition. For this evaluation, there is no limits in terms of the data that teams can use to train their data sets. They can use any publicly available or a proprietary data set to train their systems. Examples of publicly available data include the data sets that are available through the PACT consortium. For system development and hyperparameter tuning, we put together a small data set that we sampled from our test set. And to create the test set, we defined several conditions. Some of them are listed here. As you know, the GAIN protocol, the Google Apple Exposure Notification Protocol, samples the Bluetooth chirps using a 4-second window, let's say every 5 minutes. For this evaluation, we wanted to see what's the impact of that step size. Instead of every 5 minutes, what happens if I sample every 10 seconds or every 20 seconds and so on. And also, based on the previous presentation, we saw that the phone carriage state and the pose of the subjects can have a significant impact in terms of the attenuation that we measure and mapping it to the distance. Therefore, we define known and unknown phone carriage states and poses. And finally, we define fine grain and coarse grain subsets based on the binning of the distances that I will define in the next slides. Here we see a description of our evaluation dataset. It was extracted from a dataset that is available through the PACT GitHub. It is called the MIT matrix data that was collected using the MIT Lincoln Labs structured contact tracing protocol. There is a document that describes the protocol. It is available again through the GitHub address that is at the bottom of this slide. This protocol really tries to simulate some real world conditions with variations in terms of the distance between the phone pairs, the orientations. There are 8 different angles that is considered between the phone pairs. There are different phone carriage states. Phones are carried in hands, pants pockets, shirts pockets, front and back, as well as pairs. And in terms of the subject poses, they are either sitting or standing, and there is also variations in terms of the phone models. By the way, all the phone models that were used to collect this MIT matrix data set, they are all iPhones. And the dataset not only contains Bluetooth Low Energy RSSI measurements, but also inertia IMU measurements. And in total, there were 10 sessions collected using the Bluetooth proximity app that was collected also by MIT Lincoln Lab. So we took the original data set that was the MIT matrix data set, and we created our own test data sets. And to do that, we had to do some normalizations and some binnings. For example, we normalized all the different pocket locations, for example, shared and front pants and back pants pockets. We called all of these as just pocket. We also classified purse as pocket. And we ended up with these 4 different classes. Hand, that means receiver and transmitter are both carried in hand. Hand pocket, pocket hand, and pocket pocket. We also binned the distances between the receiver and transmitter to create 2 subsets. One is called fine grain and coarse grain. And again, it's obvious based on how close these distances between the 2 phones are in these 2 sets. One is much more granular and the other one is less granular, hence the names. And we extracted 4-second looks or windows using variable step sizes, which I explained before. For performance measurements, we use a weighted average of false reject and false alarm probabilities. False reject is also known as the miss detection, so we call it miss. These are defined, the probabilities are a function of the detection threshold, and they are defined in this slide. The lower the value of this weighted measure, the better the performance. And we weight the 2 error probabilities the same, so we just use the weight of 1. To run the challenge, we use a web platform that we reused, basically repurposed a web platform that we use in our other evaluations. This is a fully online and automated evaluation management platform. It supports both front-end and back-end services. The services that are supported include evaluation registration, data license management, software and data distribution, submission uploads and scoring, and results rendering. And it also supports a leaderboard. People can upload up to N submissions per day, and they will receive feedback in real time. For the for too long challenge, the N was set to 5. In terms of the participation statistics, here is a heat map of where our participants come from. They are coming from around the world, different countries, from India to Spain, UK, Argentina, and the United States. We have 11 teams registered so far. The teams are formed by 14 sites, 7 of which are from academia, and the other 7 are from industry. Here, I have some initial results. These are as of today. We have seen a significant progress over the past 3 weeks or so. Results are in terms of the normalized DCF, our primary metric, which I defined a few slides back. And these are defined for the 2 subsets, the fine grain and coarse grain subsets at various detection thresholds. Now we should take these results with a grain of salt, given the disclaimer I've included at the bottom. This is a preliminary data set. It has limitations in terms of the size and available real world variability. But we believe that it serves the purpose for this pilot evaluation. In terms of future plans, our goal for this pilot was to foster research in proximity detection and measure the performance of the state-of-the-art proximity detection techniques using BLEs, using a preliminary initial data set. The initial data set, as I mentioned, it has limitations. So we would like to use the results and analysis and feedback from this data set to refine our design for future evaluations. As Doug mentioned, we have planned a virtual workshop for late August. So we would like to invite you all to participate. I think we will circulate the schedule and announcement through the packed mailing lists. If you can participate in the evaluation, we would like to invite you to participate and contribute and help advance the proximity detection technology. And if you have data sets available, please contribute data sets. There is a link available here. And finally, last but not least, I would like to thank all the MIT Lincoln Lab staff who participated in the data collection effort. In particular, Monica Montanari and Jen Watson of MIT Lincoln Labs for sharing their insight and analysis, who helped set up this evaluation. Stacy Zeter for her help with the Bluetooth proximity app. And finally, Christine Daniloff of MIT News for sharing and allowing us to use her graphic art for the website logo. And with that, I would like to again thank the organizers and basically see if there's any questions from the audience.
Yes, thanks for your great talk, Omid and Doug. Indeed, it's a very interesting challenge. I will definitely take a look at it. Of course, I'm not well versed with this challenge, but sounds really interesting. Yeah, sure. Thanks again.
Thank you. Thank you.
Okay, then we'll move to the final end of the session. So I'll share my screen. So hello once again, as now we have reached the end of the session. So as a closing remark for today, we sincerely thank everyone for joining this event and for putting all this effort for making these great presentations. Again, for the future of internet, we must create the new ethos of responsible data. And to do that, we need everyone to demand and enable responsible data. If you have any question, feel free to reach out to us, in particular, Don and Ramesh. I would again like to thank the whole organization committee. Without them, it was not possible. A special thanks to Don and Ramesh, and that's the whole organization committee. Thanks once again. Finally, we are excited to stay in touch, and feel free to join us on both Slack and Twitter. You can find these links on our website. And finally, what I would like to say is that I would like to invite you upon tomorrow, which is the last day of the event, where we emphasize on state-of-the-art technologies for privacy AI, such as split learning, federated learning, and also the non-technical aspects from the policymaking side for responsible usage of data. And that's the ending from my behalf. And basically, yes, thanks.